to you about one of the ways that we detect planets on other stars, what we call exoplanets. I don't know if you caught the kind of intro slides that were scrolling while we were all sitting and happily drinking our beers, but we now know about more than 3,000 exoplanets. And there are two main ways that we detect those. So the one that I use, what I'm going to be talking about today, is something called radial velocities. So we'll start with that method and then get to the idea of robotic telescopes towards the second half of the talk. So, there we go. Okay. So there are three main concepts that go into the idea of radial velocity science. And the first one is the idea of dispersion. So who has ever had a sun catcher like this that you hang in your kitchen window? Hands? This is a familiar concept? Okay. So, as you might have noticed, you have one of these, you hang it in your kitchen window, the sunlight comes through, and what happens is that that prism takes the light and disperses it into a rainbow. And then those rainbows end up on your walls or on your cat. But you can see that we take that white light, we split it into a rainbow, and we can look at those different components. Now, the telescope that I use, which is called the Automated Planet Finder, does this, but on a very precise scale. So what happens when we look at a spectrum of the sun, and this is an actual spectrum we took of the sun, taken by B.J. Fulton, who's another astronomer that's maybe not here, but at the conference, is that you notice that same rainbow, that same progression from red down to the blues and indigos and violets. But on top of that, there are also a bunch of these dark lines that show up. And those are what we call absorption lines. And they're the fingerprint of the star that you happen to be getting that rainbow from. And so they happen because in the center of the star, it's really hot, and you produce this very nice solid rainbow in the interior. But in the outer, cooler layers of the star, it's actually cool enough for atoms and some molecules to hang out. And as the light tries to leave the star and make its way to us here on Earth, those atoms and molecules grab little bits of the star. They take them away and they leave these black lines that we call absorption lines. And every element, every molecule has a specific fingerprint. So if you look at a spectrum from a given star and you know that there are two black lines right in the green part of the spectrum, then that's how you know there's magnesium there. A different set of red lines in the red section tells you there's hydrogen happening in the star, so we can actually back out what those stars are made out of. And that's interesting. People spend entire careers mapping out exactly what those lines are and where they exist. And I'm really glad someone does that. I'm also really glad it's not me. It's a lot of just staring at little tubes of gas in a lab. Because the reason I like these lines is that they start moving at some point. So the third concept that happens in Doppler velocities is you have a Doppler shift. Now, does anyone know what the kind of everyday example of a Doppler shift is that we've all experienced?
Trains.
Trains, yeah. So a train, a police car, a fire truck goes by you, and as it approaches you, the pitch goes up, and then right as it passes by, that pitch drops back down. So that's what we call a Doppler shift, and that same thing happens with light. If you have a light from a star, and that star is moving towards you, the light actually gets higher frequency, gets a little bit bluer. And if the star is moving away from you, you get longer frequency light, it turns a little bit redder. Okay? So what happens if we combine this with the idea of those absorption lines is that we have that rainbow fingerprint from the star with our dark lines. If the star happens to be moving towards you, then those lines all shift a little bit to the blue side. And if the star is moving away from you, those lines all shift a little bit to the red side. Now, most stars in space sit around kind of minding their own business, and those lines don't really go anywhere. They stay pretty static. But if you happen to have a planet orbiting the star, the gravitational pull of the planet actually tugs on the star, and the star has its own little hula hoop motion in the middle of the planet. And so we can actually see that. We can monitor those absorption lines. What happens if we put all of these concepts together is that as the planet goes around the star makes its own much smaller interior orbit, and we can monitor over days or weeks or months or years worth of time how those lines in the star spectrum move back and forth. If we map those lines, again, over many, many days, weeks, months, years, you'll note that they do this kind of periodic shift back and forth. And if that motion is due to a planet, that shift looks like a sine curve. So in this plot, this is the time in years, and then the speed of the star. So based on how big that shift is, we can tell how fast the star is moving. And you'll see the star come towards you, and then away from you, and then towards you, and then away from you, over and over and over again. And if you see this kind of sine curve, you can actually back out information about the planet that's causing the star to make that little hula hoop motion. So based on how high the sine curve is, this amplitude here, we can tell how massive the planet is, how much it weighs. And And based on the period of the sine curve, or the point, or the space between the different peaks, we can tell how long it takes the planet to go around the star, and from that tell how far away it is. Now, it would be really great if when we took data like this, radial velocity data, it looked like that sine curve. I would write infinite papers if all of my data looked like this, because you glance at that sine curve and you pull out all of these characters for the planets, and you're done. Unfortunately, that's not how things work. If we look at an actual set of data taken of a star called HD 141399, because astronomers are really great at naming things. This is actual data, so the blue points were taken with the Keck telescope down in Hawaii. The red points were taken with the APF telescope, which is what I use. It's located in California. And you'll note that the squiggly line that fits all of that data doesn't really look like that nice sine curve we saw a minute ago. And that's due to the fact that this star doesn't just have one planet orbiting it, it has 4. So at any given point in time, there are 4 different planets pulling that star in 4 different directions with 4 different amounts of force, and that poor star is sitting in the middle of all these planets doing the world's most awkward jitterbug trying to keep up with all of this. But what happens is once we realize there's more than one planet, we can actually fit them all individually, and we can break out the individual planets, and then we have these nice looking sine curves, where I can once again say, oh, this planet, has a certain amount of mass because of how big the sine curve is, and a certain period based on what the period of the sine curve is, so we can actually break down the systematics and understand what each planet is doing around that star. So this system in particular looks something like this. So the red lines here show the orbits of those 4 planets, and then they're plotted on top of where our own solar system planets are. So the sun is in the middle, but not shown because it would kind of blow everything else out. But in the black dotted lines, we have Mercury, Venus, Earth, Mars, and Jupiter. And then the 4 planets here are HD 141399 B, C, D, and E. Remember, great at naming things. Very important skill for astronomers. And so what we see here is actually that it has kind of a similar architecture to our own solar system. We've got 3 planets that comprise this kind of inner, tighter system, and then a big space, and then 1 planet further out. Now, all of these planets are roughly the size of Saturn or Jupiter, so these aren't similar to our terrestrial planets, things like Earth and Mercury and Mars on the interiors. This is much bigger planets, but the spacing is kind of the same, which I think is interesting. Now, the traditional way to do radial velocity science, to get all of these data points that I showed you earlier, is to sit at a telescope all throughout the night, and one by one, point your telescope at a star, and then you just kind of hang out and look at it for somewhere between 5 minutes and an hour. So it's a really time-intensive process. You can only look at one star at a time. And so if you look at the data sets that we use to detect these planets, they span decades. Right? So when we started taking data on this star, I was 10 years old. Okay, so I had nothing to do with the science up until like here. But if you want to detect planets that are on 10-year orbits like are on Jupiter, you need to study the star for at least that long, if not notably longer. So moving forward, we're actually looking for ways to do the same kind of science, but without having to make people sit at the telescope all night. Because it turns out if you stay up all night running a telescope, it's a little bit harder to then do useful science in the morning. You get a little bit sleepy. And so the way we do that is actually to start trying to design robotic telescopes. This doesn't actually exist. I really wish it did, because I would buy this thing in an instant and set it up on my desk. But this is, okay, not quite the idea we're going for, but designing telescopes, sending instruments that can run themselves throughout the night so that we're not stuck running them ourselves. And so to do that, I use something called the Automated Planet Finder Telescope, or the APF. It's located at Lick Observatory, which is in California, kind of in the Bay Area, more or less. And it's this little dome right here. And so inside that dome is a 2.4-meter telescope, so it's roughly 7 or 8 feet tall. The primary mirror is taller than any of us in this room. And it was specifically designed to look for planets around other stars, and to do it in this automated way so that no one had to stay up all night dealing with it. Now it turns out that when I joined my science team and started working with this, they kept telling me, oh, in 2 months, fully automated, you never have to do science again. But just for right now, maybe you could stay up all night. A year and a half later, that was still the story they were pitching at me. And so at that point, we kind of decided that we were going to take this into our own hands because I wanted to, be able to sleep or at least have a social life again. So nowadays, the APF does run itself. And it does that by taking into account a big set of parameters that are kind of how a human would think about observing stars. So there are things like human input, so the precision that we want on the star, how accurately we want to measure it, the cadence that we want on the star, how often we think the telescope should go look at it, the priority, how scientifically interesting we think that star is based on suspected planets or interesting activity that's happening on the star. There are things about the star itself, so what color it is, how bright it is, because observing faint stars is harder, it takes longer. And then things like the RA and depth, or where it is in the sky. You don't want to observe stars that are right at the horizon. There's a lot of air and atmosphere between you and the star that gets a little tricky. So we want to look at them when they're right overhead. And then there are current conditions. So what is the atmosphere doing right now? How much is it moving around and making it hard to get the starlight into your telescope? What the slit loss is, so how the seeing affects what's coming in, and then the date, which we use as a proxy for how well our mirrors are doing. Because over time, they get little bits of dust and ash on them and they degrade. And so there's this big long flow chart that describes what we call the dynamic scheduler, but this is basically the software that I designed to help the telescope run itself. So I wrote down basically everything I would do in a given night to look for planets and then train the telescope to do that in my stead. It's been doing that pretty successfully now for quite a while. And so one specific example of this is a star that this hasn't actually been published yet, I think. Almost, like this week or next week, yeah. It's been submitted, it's been accepted, so you're a little late, but sorry guys. It's coming out soon. It's a star called HD 3167, and so this is a star that was observed by NASA's K2 satellite, which is another kind of planet detection, something called transit planets. So the idea here is that you can look at a star and note how bright it is, and then if there are planets that go in front of that star, you'll see the brightness of the star go from being very steady to having these dips in them. And based on how big the planet is, the size of the dip differs. You can back out the size of the planet compared to its host star. So when K2 looked at this star, it noted two planets. It's one planet that was like 1.5 times the size of the Earth. It took roughly a day to go around the star. And then another planet that was 3 times the size of it, so notably bigger, that took around 30 days to go around the star. And so we wanted to confirm that these signals are real, make sure they're real planets, and then try and figure out how much they weigh. Because one of the interesting things we do with planets nowadays is not just detect them, but try and figure out what they're made of. And to do that, you need to know how big the planet is and how much it weighs, so you can back up the density of the planet and figure out if it's mostly iron or rock or water or big fluffy atmospheres of hydrogen and helium. So we took this star, we observed it with a bunch of different telescopes. So APF, the one I use, High-Res and HARPS North. These are telescopes located in Hawaii and Spain. And this is a few months worth of data roughly. All the data points are shown here in the colored points, and then the blue line is the fit to this, so it shows you how we think the planets are affecting the star. And what we noted was that when we looked at this set of data and looked at the periods that were very strong in it, so where we think the planets are pushing on the star, and we removed the 2 signals from those planets that we knew about from K2, there was still this really big peak in about 8 days. But if we fit that out, then there's nothing. So very strong signal left in the star. It doesn't correlate, doesn't line up with any other thing we would suspect, so the star itself being active or weird effects from how we observed it. So we think this is actually a third planet. So there's that 1-day planet, there's that 30-day planet, and then in between them is a third hidden planet that K2 didn't see. It doesn't pass in front of its star because it's on what we call an inclined orbit. Instead of being straight on, the planet orbits a little bit like this, and so from Earth we just can't see it. So by doing this follow-up, using these radio velocity telescopes, we learned there's actually a third planet in the system, and that changes our understanding of how those planets might have formed and evolved. So we can take those planets now, the ones that both transit and get detected by radio velocities. We can put them on what we call a mass radius diagram. So it's the mass of the planets on the x-axis and the size of the planets on the y-axis. And then based on where they fall, we can show lines that represent where planets would be at a given mass and radius. If they were made entirely of rock, like this thick kind of teal band here. If they were made entirely of iron, which we don't really think can happen, but it's an interesting check, which is the dark green band here. Or if they had something like 25 or 50 or 100% water, so the water world, which are the dashed bands up here. Anything above that are planets where they have big fluffy atmospheres that are making up a large part of their volume, of their radius, but not necessarily much of their density or the mass component. And so this is the kind of science that we're really excited about going forward, is to look at these planets and try to figure out what they're made out of and how they might have come to be around these stars. Okay? And so this is where the combination of these big space missions like Kepler and K2, which have been in the news, and the upcoming TESS mission, can be combined with these automated, any radial velocity telescope, I'm partial to the ones that are robotic and run themselves, down on the ground, and help us to understand this new regime of exoplanet science. Okay, and so that I will say thank you very much and ask if anyone has questions.
So when you were talking about not being good to watch the planets when they're low on the horizon, like did any of the robotic things use adaptive optics, or is that in the works? Or
that is a thing. So the easy thing we do right now is we have software that says don't do that. So there are plenty of stars we're interested in observing. Let's target the ones that are right overhead. We also have instruments, pieces of hardware called atmospheric dispersion correctors that help with that as well. But yeah, we can use adaptive optics to look for planets. It's only starting to really come online. There are a few instruments being built right now that are going to use that concept. But it's not quite something that we've done so far. But like, there are talks literally this afternoon about exactly this idea at the science conference. People pitching this idea and telling us how it's going to revolutionize all of exoplanet science. So I'll get back to you and let you know if they were right. Other questions? Yeah.
So anytime we have talks about, robots and AIs, what is the chance that, Skynet's going to come in and put on telescopes and just start doing strong outside?
So we got the telescope up and running, and there were a lot of comments from people like, do you want Skynet? Because this is how you get Skynet. Like, you're bringing this upon yourself. It's clever. Like, the software is very clever, and I'm proud of it for that. I don't think it's clever enough to try and take over the world. So we're avoiding the AI side of things, which is where I think that really gets sketchy. So, like, this software has a very set list of what it knows how to do and the decisions it is allowed to make. For now, we're good. Hopefully it stays that way.
Any other questions?
What's the resolution of finding a planet on with the method you're using? Is it, can you find a dwarf planet, or are we talking Earth-sized planets, or?
Sure. So it depends a lot on this. Oh yeah, sorry. The question was, what kind of planets can we find? I'm going to click back a couple slides. So that honestly depends a lot on the type of star that the planet is orbiting around.
The mass.
Yeah, exactly. So finding small planets is easier around small stars because the planets tug a little bit harder on them. You see the star move faster back and forth. So it's an easier signal for us to pick up as those lines shift. We have found planets down to roughly an Earth mass with the radial velocity method. And if you do it via transit, we can actually see planets down to a little bit smaller than the Earth now. But the big push is still looking for an Earth-like planet around a Sun-like star. That hasn't quite happened yet. But it's definitely one of the goalposts for people in this field still. Thank you all so much.